Okay, so I guess most of you know Chandra Varma, with who I've been working for many years, 25 years, something like that. He was in my habilitation of research, he was in the committee, and he's doing some theory, important theory for the ITC cuprates, and for which had been the motivation for us to work on this, on searching for the loop currents. And it was a long-term project, which is still continue, and we still have some idea to continue with that. Chandra has been the main proposer to do that and to give us more every year, something new to look at. So it was very interesting over the years. Okay, so you can start. Thank you.
Thank you. It's a great pleasure to come back here. I was here 10 or 15 years ago in Saclay, although I come to Paris often. Philippe told me to give a general survey of where I feel we are in a particular theory of the high temperature superconductivity in relation to experiments. And I've decided to speak on what remains unproven by experiments for the theory of high temperature superconductors, which of course presupposes that there are things which are proven. And I'll talk about both, and I was wondering whether I should give the bad news first or the good news first, but I decided I will give the good news first and then the bad news. But let me first generally survey what is it that we are trying to understand. Well, here is my view of the
recording. Forget that one.
Here is my view of the universal phase diagram of superconductors, of high temperature superconductors, and by that I mean that I will focus on phenomena that happens in every cuprate family, and phenomena.
Can you move a bit this way?
Phenomena that can be related one to the other. This field has been going on for over 30 years, and maybe there are several 100,000 papers in it, and there are a variety of experiments. And the strength of condensed matter physics is that we can learn from experiments and correlate one with the other. So our task is to derive this phase diagram and properties in each part of it and relate the properties one to the other. In writing down this phase diagram, one should bear in mind that there is an experimental way to measure the energetics of the important changes by thermodynamic measurements of specific heat or magnetic susceptibility. And from that point of view, there is the half-filled antiferromagnetic region, which I will not speak about, but which should also be given by the same model with which we treat the rest. There is superconductivity. Then there is something that we did not know in the early days of ITC, but we know now. There's another line where every property changes. And from the entropy change here, we know that somewhere around here, the change of energy going from there down to, let's say, the superconducting transition temperature is twice or thrice the change in energy from the superconducting transition. So this is a major effect, and you can measure it here, and it becomes superconducting, and you have to destroy superconductivity with magnetic field or something to continue this. Similarly, in here, there are remarkable properties. To continue down to low temperature requires some technique to reduce superconductivity. And then there is what I will describe as a crossover. Now, I have been led by the belief that everything interesting that happens in this region should be driven by one important principle, and everything should follow from it. That's a prejudice. And then to say that one has a theory, we should be able to derive these properties systematically, and if possible, have independent and verifiable predictions. Now what? Okay. So I drew that central region, and this is going to, this has played a very major, the major part in my thinking, that anything you measure in this region has remarkably simple properties, but properties we had not come across in condensed matter physics before. And it, in particular, there's no way that we can understand the properties there by any of the ideas of quasi-particles and Landau theory. Let me give you an example. Several examples here. If you measure the resistivity there, which is the most often talked about thing, there is a constant part which you can vary by varying the impurity content. There is a linear in T part, which I'll show you, and this coefficient B is within about 30%, the same in all cupric families, and this coefficient does not bear a relationship to the coefficient A. You can vary impurity content by an order of magnitude, changing A by an order of magnitude, and this does not change. Corresponding to that, there is a conductivity which I've grossly sketched, removing the impurity component, goes as 1 over omega log omega. There's a Raman scattering, which goes essentially as a constant up to some energy. The tunneling conductance, which goes as modulus of voltage. There's a nuclear relaxation rate on copper, which has a leading term, which goes as a constant. Now, there are some peculiarities of Hall effect. Let me just go back to this idea that this cannot be a Fermi liquid if this T is going all the way to zero temperature, and we have now cases where it's going linearly in T with essentially the same slope from 1 degree to the temperature where this compound melts. Now, there's a general idea that resistivity scattering rate has to be less than the single particle scattering rate. So the single particle scattering rate is going as T or omega, and particle energy is going as T or omega, so that there is the scattering rate or the inverse lifetime and the energy are the same. It cannot be a lambda quasi-particle. That's the simplest way of stating my proposition. So here's an early measurement, already in 1996, of a compound whose TC was 7 Kelvin. Okay? And the resistivity, this is experimental data on that one. And now we have lanthanum, doped lanthanum cuprate, where you can reduce TC to about 2 Kelvin, and you can see that this thing persists. This thing changes when you go to this part of the phase diagram. For example, here is data in lanthanum strontium cuprate, and in this region you have this linearity. How linear is it? Let's take the derivative d rho over dt, and that's what this is doing. And then as you cross over into this region, the resistivity begins to change, and I've roughly marked this boundary. So in here also the resistivity is linear for some temperature, and then it does funny things. And here's the derivative. You can see that more carefully, this boundary of this change. I have purposely not continued this dashed line further because we don't really know. Samples become dirty and different materials begin to behave somewhat differently there. Okay. I mentioned this thing about the thermodynamics. Now, I will use this thing that you've heard about, pseudo-gap phase, which was first discovered by Henri Alloul here through night shift measurement. Okay? So night shift is supposed to be roughly a constant, but in this compound, or the magnetic, let's say here is a thermodynamic measurement, which is somewhat related to the night shift. The magnetic susceptibility was roughly a constant for dopings near that doping in that dome, and then it began to change at some temperature, and the temperature where it began to change is that line T star that I drew. This is this and this are the same. These are deductions from the measurement of specific heat by Loram in bismuth 2212, and you find again S over T, which should be a constant. There is a interesting small increase there, I might speak about, but there's a definite temperature where it begins to change, and in fact, you can put this and this plot essentially on top of each other. Okay? So entropy and magnetic susceptibility are behaving similarly. And here's an interesting plot. If you look at the jump in the specific heat at the superconducting temperature, it begins to diminish around the doping where the linear resistivity is dominantly seen to the lowest temperature, and it begins to decrease. This sort of suggests that this loss of entropy already in the pseudo-gap phase is reflected. You've already lost some electronic degrees of freedom, and it's reflected in having it's a measure of the superconducting condensation energy in some sense. And TC is doing something like that. Yeah. So I'm giving you the basis for that phase diagram and the important changes. And let me again say that if you look at something like that and integrate, you see, specific heat is d over dt, derivative of energy with respect to temperature, so you can integrate the specific heat and get out the energy change, and that energy change in this range is significantly larger than the superconducting change. Okay, so very early on, by looking at all these different properties, some colleagues of mine and I suggested this suggestion was already made by Anderson that this could not be a Fermi liquid, and we suggested a remedy. What is happening instead of a Fermi liquid? Now, there are lots of ways of thinking about a Fermi liquid, and to me the most useful is that any response function you study, the charge fluctuations, spin fluctuations, current, anything you do, because of the Pauli principle, it decreases linearly with omega with some cutoff scale, which is essentially related to q times the Fermi velocity, or ultimately the Fermi energy. And then there's this cutoff. And all Landau theory basically does is to give you, for different response functions, slightly different slope, which can be related to the Landau parameter. But the fundamental fact is already evident in the non-interacting theory, that due to limitations of phase space by Pauli principle, the spectrum decreases. Now, this, by general causality, has to be an odd function of omega, so sort of going like that. And given this, you can calculate the scattering rate of fermions. It'll go as t squared in the single particle scattering rate, and if your material is such that there is some Umklapp scattering, then you will get a resistivity proportional to t squared with a different slope than the scattering rate. It's good to remember that in the pure limit, if there is no Umklapp scattering, the resistivity is zero at all temperatures. Okay? Not just the limit of zero temperature. Umklapp, you have to lose momentum for transport, for resistivity. Well, obviously this was not working. So a bunch of colleagues and mine and I proposed, it's good to remember that a Fermi liquid is also a scale invariant theory. The fluctuation spectra is going as 1 over tau squared, where tau is, let's say, if I'm at t equals 0, tau is just the time, otherwise it's a periodic function of temperature too, okay, at the final temperature. Okay. So this is 1 over tau squared, and we in effect said, let's try some object which goes as 1 over tau, which is much more, which is quite different. You should think what would happen if the spectrum goes as log of tau. If there's log of tau, there will be ground state entropy. It's forbidden. If you believe in the third law, which I don't really do. Okay, so if you now Fourier transform this, the imaginary part of this object goes as omega divided by temperatures. There's no scale in the Hamiltonian, and then it will become a finite value until you put some cutoff or a short time cutoff for tau c, or a high frequency cutoff for omega c. And it is possible to show very easily, at least perturbatively, that the scattering rate from this will be proportional to omega over t, and if one believes again that there is Umklapp scattering modulo a coefficient, and it has taken me 20 years, 25 years to calculate that coefficient. I'll show you the result, how the resistivity is related to the scattering rate, and all these properties that are observed follow. Now, there's a very amusing mistake here, which was rectified much later and we had a microscopic theory for this. Here we assumed that this object is Q independent, and it was because there are experiments done here which probe different parts of the fluctuation spectrum, different frequency range, different momentum range. For example, nuclear relaxation rate measures very low frequency, the leading omega term integrated over Q, and this thing gave us the same answer as we needed for, let's say, Raman scattering, which measures Q equal to 0 as a function of omega. Okay? So this was assumption was made. But this object, you can take its real part, Kramer's Kronig, and that will be a log of omega or temperature. This has to be an odd function again, as I mentioned. So you see, all that we are doing as we go to lower temperature is to pile up the weight at lower and lower energy, and in the limit of t going to 0, there is a discontinuity. Therefore, the Kramer's Kronig gives us a log. A log of t means that there is some criticality in the limit of t going to 0. Okay? Now, we could also predict that the specific heat from that will be not linear in T like in Fermi liquid, but will go as T log omega C over T, or thermopower will also go as T log T. Specific heat behavior in the cuprates spike has been only measured in the last 3 or 4 years. The group of Thomas Klein at Grenoble on samples by Lee Taifer in Sherbrooke, and this thing has been is found. And very importantly, I got confidence in this idea only when the single particle scattering rate was measured, and that happened about 10 years after proposal, when angle resolved photon emission was developed as a quantitative technique. But we are saying there's a critical point at t going to 0. So the question is there a symmetry breaking? Is there a point, the critical point, the critical phase, etc.? And we have to answer the question, what is the symmetry breaking, such that the fluctuations of that phase lead to this spectrum. And this spectrum is very unusual. You're not going to get this spectrum out of any of the extensions of the usual theory of phase transition, Wilson, Fisher, Landau, Ginzburg, etc., taken to the quantum regime. They will give you a fluctuation spectra which goes on peaking near omega going to 0 as you approach the critical point. Here, all that is happening is that this edge is moving for the bulk of the spectrum remains the same. So this is a very, very curious and different kind of criticality.
Okay, I mean, this problem of the critical point, quantum critical point, is it's an assumption. I mean, nobody discovered this point. I mean, it's only because of the scaling, you assume that there is a second order quantum transition, I mean, with some order, some breaking of symmetry. It's a pure assumption. I mean, there is no proof that there is a quantum critical point.
But this is quantum critical regime.
I think it could be something else.
I think you're right. I am only a poor physicist, not a mathematician, and I'm going to make some assumption with which, if half a dozen different experiments are understood, I'm going to say that's pretty good. Okay?
Yes.
That's my way of doing it.
No, but normally, I mean, here the problem is hidden under the. I mean, it's not easy to reach this point. To really.
Yeah, you have to do experiments. To reach this point, and as I mentioned, supposing you suppress superconductivity and the properties that we were following from, say, 700 degrees to 40 Kelvin, continue down to 1 or 2 Kelvin, then I would say, hey, that looks pretty good. Okay? I'm not going to ever reach absolute zero, and I'm never going to be able to satisfy you, if that's what it takes to satisfy. Okay, so I mentioned this thing about linear scattering rate. Okay, so certain things can be done systematically to low frequencies. So this thing came about through technical developments in angle resolved for emission. And this is the momentum distribution curve half width normalized to the Brillouin zone size as a function of energy at some temperature of the order of about Tc, okay? And then you have measured it to low energy, and this is predicted to go as T for T smaller than omega, and to go as omega larger than T. And these are all the 4 compounds which have been measured by various people, and you find that the scattering rate within some error bars is linear, and then it saturates. And there is this slope, and there is this cutoff, okay? And the cutoff is on the scale of 0.3 to 0.4 eV, and if I take the sensible Fermi velocity to convert that also into energy units and get the slope in dimensionless units, that slope is varying there between 0.4 and 0.5. Okay?
So again, what it is, for which doping, what is the regime?
Very good point. I think I have written here. These, for bismuth 2201, bismuth 2212, it is at the optimal doping and in the nodal direction. For lanthanum strontium copper oxide, the optimal doping is about 0.19 or 0.20, and it's 0.15. And this is lanthanum strontium copper oxide 0.17, and not the nodal thing, but 20 degrees away, 20 degrees away from the nodal direction. Okay, and the resolution of the experimental data gets worse as you go away from the nodal direction because of the experimental background, but you typically find that there is less than a factor of 2 difference in the slope going across. So to a first approximation, the scattering rate is independent of the angle, and in fact you can relate it purely to the fact that the Fermi velocity in the antinodal direction is smaller, the density is higher than the nodal direction, and if you extrapolate that for a circular Fermi surface, one would say it's likely to be the same. Okay, so what I can tell you is that given these 2 parameters,
Chandra, just to understand this, that the LSCO is in the nodal direction, and then the angle is
there
varying?
are 2, LSCO 0.15 in the nodal direction, and green is LSCO at 20 degrees at 0.17.
Okay. And of course, it's above TC.
Yeah, both are about TC. That's good. Okay, so the important point I want to make is that the 2 parameters here, and I can get you the coefficient of the linear heat capacity, the coefficient of the linear resistivity, the coefficient of 1 over omega of the conductivity, and a couple of other properties. It's in a review of modern physics in terms of these 2 parameters, okay? Quantitatively. I think this is just short of what was achieved when people started trying to test Landau Fermi liquid theory in liquid helium-3. Okay? So there is meaning in these parameters.
I would like to be cautious about the fact that, for instance, in IPCO 7, the linear term of the resistivity, if you extrapolate it from high temperature, would be negative.
Absolutely.
Which means that it turns over somewhere.
Absolutely. That means that the data is not at the critical point. That is, all this thing is expected to be quadratic in this regime, and there is data for 3 or 4 of them where the resistivity is quadratic, and what we are really discussing then is a kind of slightly higher order theoretical point, what is exactly the shape of this crossover function. Okay, so that's just phenomenology, but we want to derive things. Okay. Now, there have been two quite different approaches and manner of thinking on this problem. What I call the great theoretical schism. This is almost a joke because this is where two different approaches which one can give some credit for, and which took some 75–80% of the people. Here was just me and my collaborators. There were also some much crazier ideas, okay, which we will not talk about. So, within a few weeks of the discovery of high TC, Anderson decided that at half filling these materials are not anti-ferromagnets. I can tell you amusing stories about this. We were at a conference together in Bangalore, in India, on the December between Christmas and New Year's in '86, and there was a guy at Bangalore by name C.N. Rao who had been making powdered samples of lanthanum strontium copper oxide, but being a poor chemist, he had never cooled it, he had even doped these things, he only had liquid nitrogen, and we all went to his lab to look at the data, and he showed us the measurement of the magnetic susceptibility. Anderson looked at this magnetic susceptibility and said, look, it's not an antiferromagnet, it's smoothly varying susceptibility. So 2 days later in the morning, Anderson announced to the conference organizers that he had solved the problem of high TC and that he would like to give a talk. And that was his science paper, which appeared in January of '87. Before that, we had a conversation in Bell Labs in which Anderson was saying, and this is a very, very profound guy who invented the field of antiferromagnetism in some sense, and lots of other things. And he said, I have never known a spin-half antiferromagnet. Okay? And so you could see how the wheels were turning. Anyway, so he said that the problem is the Hubbard model. Half-filled, it's RVB, and then the physics changes when you dope it, and RVB state turns into a superconducting state. There's no reason for anywhere to be a Fermi liquid. There was an alternate point of view which I should have been a part of, because just the previous few years I've been working on heavy fermion antiferromagnets and suggested that antiferromagnetism will lead in them to D-wave superconductivity, but I avoided that easy trap. But there is something very amusing about it, because for two-dimensional antiferromagnets, the criticality seems to be identical to the criticality that I'm going to speak about. It is not at all of the Wilson-Fisher kind. Okay? And that there's an amusing story there. So the alternate point was, to wait for a year or two, discover that a half-filled case is an antiferromagnet, and to think about in terms of a quantum critical point and quantum critical fluctuations, and the belief that what you need is a more general model than the Hubbard model, and to discover unusual ordered phases, and from there derive the quantum critical point and quantum critical fluctuation. And that's the path that my colleagues and I took. Now, in order to make a model, you have to understand some chemical properties of these materials, okay? And it's necessary. Now, for some strange reason, I had found out already in the early 1980s this remarkable fact. It was because somebody had shown me data that the chemisorption energy of simple gases like oxygen, nitrogen, nitric oxide, carbon oxide, etc., vary in a systematic fashion as you go from the left to the right of the periodic table. And I discovered that they could be correlated to the affinity energy of the transition metals, the energy to change from 2+ to 1+, and where the ionization level of the gas lay. For example, for oxygen, it would be going from O2- to O-. And I knew that this line crossed around copper. Okay? And this is easy to understand in elementary atomic physics. You're increasing nuclear charge, but the extra electrons are not screening the nucleus completely. Therefore, for the extra charges, the energy gets deeper. Okay? And this was already enshrined in something called the Zanen-Sawatsky-Allen knowledge about the transition metal oxides, that if you try to understand the details of the exchange energies, you cannot do them just on the Howard model. If you say U is the repulsion and W is the bandwidth, then and another parameter, which is the change of energy from copper to oxygen, which I just talked about, divided by the bandwidth, then you can draw a boundary, and these they call charge transfer insulators, and these they call Mott insulators, and these things here would be metals. Nickel sulfide is an itinerant metal. For example, sulfur, the levels go up compared to oxygen. So, there's one important, I think, important change that I made. This affinity energy and ionization energy are defined with isolated ions, but we are dealing with a solid. And if these energies are close, this difference is close, we have to very importantly include the interaction energy between the copper levels and the oxygen levels. Okay? Because they're going to control the charge fluctuation. This will become an important parameter when this energy difference is small. Okay? So this was also kind of present there in Lenny Mathis did the band structure of copper and oxygen cuprate within a month of the discovery, and you see that the copper and oxygen levels are completely intermixed here. If you were to do it for, let's say, vanadium oxide, you'll see vanadium levels here and oxygen levels down there with the 3 or 4 volt energy difference. But here they're all mixed in. Okay, so this kind of chemistry knowledge, I'm proud to be a chemist when it's necessary, made us feel that Schmidt-Trink and Elliot Abrams and me, that the model should be copper and oxygen orbitals, so there will be 2 oxygen orbitals, and besides the local repulsion, the interaction between these things. And when these energy levels in this are close, there's no way this can be reduced to a Howard model. Okay? All that Jang-Grice business becomes complete rubbish. You're doing a perturbative calculation of the denominator of close to 0. Okay. So the thing to do, and especially in the mid-1990s, when thermodynamic experiments showed that there's a big change at T star, which I showed you very early on, sort of looked for all possible transitions in the dope charge transfer model, which do not change translation symmetry or spin order. Again, based on experimental information that along T star, there was no evidence for any change of translational symmetry, and I talked to various people, including Philip, and by that time, neutron scattering had shown that the antiferromagnetic phase goes away well below, and the antiferromagnetic correlation length systematically decreases as you go towards the region where quantum criticality is important for me. So that could not be quantum critical phase. So I shall briefly describe, if people are interested, the physics of this loop current order which I proposed, and it was proposed to be something which would not have been detected by then. It's easy, it would be a hard phase to detect. And also, I needed a phase where there's a phase transition without a singularity in the specific heat. Okay? And this is one such thing in two dimensions. It doesn't do that. So this is a phase in which on the copper oxygen unit cell, there'll be a spontaneously developed flux, here positive and negative in each unit cell, so that you could define a magnetoelectric or Anapo order parameter, which is magnetization at a point R crossed with the vector R.
Chandra, your point is there is no randomized sequence of the whole phase diagram, or just at the optimal?
At the region where I'm interested in discovering criticality. The same model will give the same model will give antiferromagnetism. Okay. Okay. So then some experiments started coming around. But before I go to the experiment, if people are interested, I will give you a simple physics of what's the physics of loop current order. I can also skip the next 3 slides. Yes,
that's
sir.
a simpler question.
Yeah.
Where are the inversion centers that are broken? Is it all the coppers in the picture?
Yeah. So if you look at this, the only mirror symmetry which is preserved is along this axis. Okay? And if here's a magnetic field going up, and magnetic field is an axial vector. It violates, it changes, right, all reflections, and this thing does not have inversion. It has lost. This is not a point of inversion. This is not a point of inversion. This is not a point of inversion.
When it's off, what is like in the crystal structure with all the other atoms?
Yeah, most of them have centers of inversion. This one does not. After this pattern.
But before the pattern, do coppers live on the inversion?
Sorry?
Before the pattern, do those coppers live on the inversion centers?
Coppers do live in the inversion center.
Okay, thank you.
Yes. Okay. So anybody interested in my little cartoon story of loop currents?
Yes, we are.
Yes.
Okay. So I'm going to illustrate that by simple physics of a triangle. See, if you have a triangle and there are orbitals 1, 2, 3, and the Hamiltonian is going from one to the other, this thing has 3 states, a purely real state, see? Or you can have a state in which there is a clockwise current, or a state in which there is anti-clockwise current, right? And ordinarily, these time reversal breaking states will be degenerate, 2 and 1, or 1 and 2, and that depends upon the product of the transfer integrals. The product of the transfer integrals is negative, and these things lie low. And then it depends on filling. If by interactions you can lift the degeneracy and the chemical potential lies in one of them or in the middle, will break time reversal. Okay? Now, Okay, I think I said all this. Now, what we are really saying is that are there interactions which mix the orbitals of copper and oxygen non-interacting? So what are the orbitals of copper and oxygen? Well, there is an orbital which is a linear combination d plus px plus py or d minus of px plus py, the bonding and the anti-bonding orbitals of copper and oxygen. And there is one orbital which is px minus py, that's the non-bonding orbitals of oxygen, which doesn't hybridize with anything in the simple tight binding orbital. Imagine you have interactions such that these can be mixed, and they are mixed with an imaginary component or a complex component, but something with an imaginary component. That means that the new Warnier orbital is a complex orbital, d dagger plus e to the I theta px dagger, theta small, plus e to the minus I theta py dagger. And what that means is that going from copper to oxygen, you have a minor transcentrical, which means that there's a current flowing. And if there's a current flowing in this triangle, rule of life, current loops cannot flow indefinitely. That's always an unstable state. And I don't want to change translational symmetry. It means I have to change, I have to close the loops within the unit cell. Now, it turns out there are lots of ways, three different ways of changing the loops. And I, of course, picked the wrong one first, and then finally settle on this thing based on the first experiments that came out, in which current is flowing from here to here to here, and it's flowing from here to here. So there's a clockwise loop and an anti-clockwise loop, but you can see that there are four possible domains of this. Okay, and that four possible domain will play an important story. Now, how do you generate this kind of thing? Well, you can, again, you don't prove anything. Monsieur Footy will be unhappy. I'm going to make a suggestive calculation and then say, experiments, can you look for it? Okay, and if you find it, you'd say, okay, you've done something. If you don't find it, you go back and do, you change your mind and do something again. Okay, so in this case, I had this interaction, V times Ni and J, where Ni and J are operators. This is an operator identity. I can write this in terms of modulus of Jij squared plus Ni plus Nj, and the Jij is the admission operator, which is related to current on the link Ij. Let me imagine that I have an expectation value of that, that's Xij, then my effective kinetic energy is not just Tij plus, it's Tij plus Xij. You're saying there's a vector potential and the link Ij. Voila, if I make closed loops of that, I have the model that I'm talking about. Okay? That's the physics of this. Okay, so then the experiments started coming out. I'm going to show you two experiments on the same material. The experiments were first done in Bismuth 2212 by Arpis, okay, by Kaminsky et al. But neutron scattering in principle gives you the most detailed, information. In practice, bloody hard, because I'm not changing translational symmetry. Okay, so I'm getting some magnetic signal at the same sum of the same Bragg spots where there is a nuclear Bragg peak, which is for the kind of moments we expect, 1,000 times larger than the magnetic, few hundred times larger, and so one has to do the experiment very carefully. I think this could be done only at Saclay when there was a reactor here, and Philippe and his Laboratoire Léon and so on could go to the reactor anytime and do it. So you can't just go to ILL, write a proposal for a week, and discover things like this. Okay, so they did this experiment, and I'm always amazed at not that they just got the result, but they did not tell anybody, including me, that they were doing it, and they had some results till they had done it for 5 different samples with different composition. And in the cuprate game, people were, publishing anything they got new, they would publish it. But I think that comes from having a different academic tradition in France than in, let's say, America and indeed Japan or China. People are to get results. What about in England? So here was the thing, and you see that the temperature where this was happening was moving down, and then at 07 there isn't a magnetic polarization signal. And this is done with polarization analysis. On the same samples at somewhat similar doping, many years later, I think this started around 2005. This happened around 2011. This guy at Caltech, did second harmonic generation. That goes to your statement about symmetry, center of symmetry. There's great center of symmetry, there should be second harmonic generation, but doing that in a metal is not easy because the surface breaks, right. And you have to be very careful what you're doing. And they found that there was an extra signal. You see that? There's already some second harmonic generation, and then something increases, and this increase happens at a specific temperature, which, if you interpolate between these things, you'll find is within 10 degrees the same. And there are various other techniques used. For example, you can prove that if this magnetic pattern comes into being, the symmetry of the magnetic susceptibility in the unit cell will no longer be that of a square or a tetragon. Symmetry will change, and that can be measured by torque measurements, which was done here. And all these things kind of fell here, and there are some other techniques which are really not so specifically symmetry sensitive as the 4 techniques that I've described to you. And in the case of the cuprates, summing the 2 moments together, the maximum autoparameter is about 10th of a Bohr magnetron or unit cell. You had a question, did you?
It might be. I was going to say, what do you know the magnetic point group of the?
I know everything by
what's the magnetic point subgroup?
I don't remember the technical name anymore, but I can look it up.
Great.
Okay. Let me go back from this happy story to another happy story, and then we'll go to the bad news. I had already mentioned the phenomenology, and it turns out that this phenomenology has some interesting faults. You call your fault interesting if you get the right answer for the wrong reason. And that's what I mean here. So first of all, the biggest fault is we had no idea what we were talking about. In 1989, what are these fluctuations of? Now we know we have to look for fluctuations for this order parameter. Okay? We assumed momentum independence of the fluctuation and compensated it by assuming that the coupling to fermions is also momentum independent, okay, to get various properties. But this led to the prediction that the single particle scattering rate is angle independent, which indeed it is, but with my friends Miyake and Schmittering, I've proven before the high TC games began that D-wave pairing requires scattering by 90 degrees. So we predicted in that paper. Should be S-wave scattering because we expected the single particle scattering rate to be angle independent. So there is this big problem. How to reconcile observed D-wave superconductivity with this. Okay? Now, it's very easy to see that this fourfold variation, see if you neglect, I mentioned to you that this has four things, and the fluctuations I'm going to speak about, say, I'm in the quantum fluctuation regime, so I will fluctuate between these four configurations, and fluctuating between four configurations, you can imagine I can make all kinds of current patterns in the unit cell, okay? And that's what we're talking about. Now, if you could continuously go from one to the other, it would be the XY model. I have a vector order parameter which is lying in the plane. And you have to show that the fourfold anisotropy is irrelevant. It's not irrelevant classically, but it's irrelevant quantum mechanically, and that can be shown. Okay? But if you have a quantum 2D XY model, its critical properties should be just like the 3D XY model, liquid helium-3, and its critical fluctuations are phonons. And they're going to give you zero of interest. Okay? So you have to couple these fluctuations to fermion, and in coupling the fluctuation to fermion, you have to answer the question, what is the coupling function to fermions? I will not go through the proof of this, but you can show that if this is the fluctuation of this cosine theta, then this coupling function varies as I times G naught times K cross K prime, which means that at small K prime, and there's a lattice generalization of it. But it means that this vertex is really going as the cube, proportional to cube of this momentum transfer. And I say this only to annoy my mathematical physics friends. The rest is only field theory. Okay? So the hard part of the problem was the chemistry, thinking of the loop current, and rest is only field theory. Okay? Now, I'm going to do better than this. I'm going to show you what the fluctuation spectrum is, and it's by an experiment. We can derive it by some renormalization group technique, but it's much easier to show the result by taking this model with this kind of coupling to the fermions, integrating over the fermion, generating an effective new coupling, adding it to that of the XY model, and doing Monte Carlo calculation on it. Okay? So this thing has no sign problem, and this thing is Monte Carlo in the space of three parameters: the kinetic energy of the fermions, kinetic energy of the rotators, the interaction between the rotors, both normalized to the upper cutoff tau sub c, and the parameter alpha coupling it to fermion. And in the space of these three parameters, there's a two-dimensional surface at which the critical exponents are identical. Okay? That's from quantum Monte Carlo calculation, and I'm showing you one of these. So I'm varying some parameter, is coupling to the fermion, other parameters fixed, and I am seeing how this correlation function changes as I change tau. Okay? And you see that it's going down exponentially. It happens not as tau, but as tau to the half. Okay? And I cannot derive that analytically. In leading order RG will give me an exponential fall off. Okay? And then beyond some value, it goes up. And in between, it's a constant. But I'm plotting tau times g theta. So g theta is going as 1 over tau. Okay? And in fact, in our paper, I had this wonderful guy. He's compulsive. He added 2 more decimal places in here, and so we have a dense set of things here, but they only clutter up the thing. And then you find that all of these curves, up to the place where they get noisy, collapse onto a single thing where you can define a correlation length in time as a function of these parameters, and well, it's a limited region, but this thing is going exponentially as to the minus t over tau. Simultaneously, we can look at the spatial correlation length for a fixed time, and this is on a linear scale, and this is on a log scale. So to only this accuracy, we can say that the spatial correlation length is going as logarithm of the temporal correlation length. Okay, that result can be derived by analytically by RG as well. So its spatial correlation length goes as log of the temporal correlation length. It is effectively, not exactly, but effectively saying the so-called dynamical critical exponent is diverging. It's going to infinity. That's important to rectify the phenomenology that we had proposed. And it finally, I'll quickly go through this. We have to explain why the normal state self-energy is angle independent. See the particle run into particle. And here there's a Cooper pair in between for the pairing fluctuation. And you can show that if these vertices are k cos k prime, then this is only present, the fluctuations, only part of this fluctuation that is important is the S-wave part, and it's repulsive in the pairing channel, and this thing with the k cos k prime, and this thing of the form that I gave you, that it is attractive in the D-wave channel. And this has also been tested by mercilessly by taking angle-resolved photo emission data in China by Bock et al. And inverting it to get the fluctuation spectra. So now, first of all, I like to. So this is the momentum distribution curve. This is in the normal state, and if you are an experimentalist, you have to admire the quality of data that it's possible to get at IOP Beijing by having $500 million worth of equipment to do angle-resolved photo emission, besides dedicated people. Okay, and the red thing is the spectra and the superconducting state, and the information about what makes superconductivity is obtained from the difference between these two, which, of course, naturally is a lot more noisy. So if you smoothen this data and you integrate the Alyashberg equation, and you can get the fluctuation spectrum. So this is the normal the fluctuation spectrum, which gives you this normal self-energy that looks like these two curves, 90K and TC is 82K. And if you look at the pairing object, it looks like this. And I think there are errors of at least 20% in each of these. But you can say that apart from this bump which is probably due to some phonon, which I do not understand. This fluctuation spectra is a bit like what we suggested causes the whole game. Okay. Oh, finally, being a theorist, I'm very proud of this calculation, which took enormous amount of time, both mine and this guy, Hideki Maebashi in University of Tokyo. It turns out that we can solve the Kubo integral equation exactly for the conductivity with this kind of transport. This hasn't been done. So Mr. Piles in the late 1930s or 40s understood everything there was to understand about electron-phonon interaction, but nobody could derive the transport from electron-phonon interaction despite a lot of effort, including Umlauf scattering. But this fluctuation spectrum is so simple because it's a product form of Q and omega, that one can solve this problem of evaluating this thing. And what's our principal result? Our principal result is that Umlauf scattering for a circular Fermi surface at about the critical doping on a square lattice provides a numerical factor on the single particle scattering rate of 0.7508. And I had to stop my young friend, Maebashi, young. He worked with me as a postdoc at Bell Labs 30 years ago. He's 60 now. And so the point is that the Umlauf scattering does not make any temperature correction. And then you discover some additional things which you can derive, that there is no mass correction to the resistivity. There's no T log T. Specific heat goes over T log T. That does not enter into the resistivity. The no Umlauf scattering is necessary. Umlauf scattering will change magnitude, but see, without Umlauf scattering, the resistivity is zero always, but not thermal conductivity, energy transport, and there is no, even though thermal conductivity is carrying heat, the heat capacity log T correction does not enter the thermal conductivity, but it enters into the Seebeck coefficient. Okay, so that's thing. Okay, now let me tell you. I'll tell you all the good news, and I've mostly concentrated on this region and the symmetry of this phase, and now the bad news. What's been observed in the last 10 years is that not only is there a diminution of the density of states in the pseudogap phase, there is also, if you do angle-resolved photo emission, you're seeing the whole Fermi surface within the resolution that angle-resolved photo emission is carried out, you see a Fermi arc. And if you do magneto oscillations, which can see much more closely, it's not really a Fermi arc, it's a closed loop, and you have to surmise that one side of that closed loop is very robust, large amplitude, the other is very small, and how to get that, okay? So, how to get that, okay? Now, that closed Fermi surface there may be a few of them, but the one that and they are degenerate, what you measure is 2% of the Brillouin zone, whereas the whole Fermi surface is more like 50% of the Brillouin zone. So you see 2%. You see tiny pocket. Okay? And so one has to think of something, and this has been for me the hardest thing, because I'm always thinking of very complicated things, okay, for the pseudogap phase. But if one says, oh, well, the fundamental order is loop current order, and this can exist in these four directions, and why not say that the periodicity is broken, that I can make domains of this, okay? Now, one runs into, interesting physics. because you cannot make a domain of this with a domain of this without a current flowing at the boundary, because you have to conserve current. Okay? So it requires specific topology, and here is one. You can say that in this whole region, there is this, you remember my order parameter? Let's say each of these unit cells has this fellow, and then there's a boundary, and there's this fellow, and there's this fellow, and this fellow. And if I put these two together, I cannot put these without having a vorticity here, vorticity here, vorticity here, and a vorticity here. And if you look very closely here, that will be a current pattern which is different, but an allowed current pattern, where this again does not change translate. You see, this has a current loop like that, and 4 current loops like that going on to the next cell. And while this produced you Bragg scattering, which will give you 1, 0, 0, 1 Bragg spots, this produces you a half zero Bragg spot, positive and negative, and you have to go 2 unit cells in this direction to repeat. And I never bothered about it, but this was only a point, and I expected this P to be from 8 to 10, the period to be at least 8 to 10 unit cells. Okay? Now, the interesting thing about the topological aspect of it is, because these materials are dirty, they're not so very clean, especially in the pseudo-gap phase. But if I go from something like that, this property that there will be vorticity around here, here, and in fact, there'll be vortex-like feature at these, all the corners, has to be preserved current conservation.
Can I ask a question?
Yes.
Are you saying that the current along the domain walls is immune to backscattering?
Is what?
Immune to backscattering?
Say it again.
Be immune to backscattering.
Immune to backscattering.
Yeah.
This current must be conserved if in the bulk. And okay, maybe I'll answer your question another way. If only this pattern existed everywhere, this would be the equivalent of the Haldane pattern of hexagonal lattice in a square lattice, okay? Which has a topological surface current.
Right.
Okay? And that property is inherited if I terminate, if I make more corners. As you can imagine, it has to be, because it's, topological.
Right.
That's required. Okay, I don't know too many mathematical terms about this, but you can see that you have to conserve current. Okay? And that's the only way to do it. Even if you distort it like this, if you have, sinks. Okay. Now, so what we are doing is, we are taking, let's say, 20 unit cells, which means we are making our Brillouin zone into 20 by 20 little things, and then they will be scattering from one to the other, and you're going to make gaps. But if there is interaction between these current patterns, the only scattering that's important is from below the Fermi surface to above the Fermi surface. But if you look at these pockets, look at these Fermi surfaces, and look at the original Brillouin zone, so I'm looking at the original first Brillouin zone. Let's say this is the original Fermi surface, which I'll call the privileged Fermi surface. That contains the right number of electrons. Now I have Fermi surfaces which are like this, which are the squares which are in the diagonal, but they're also squares not in the diagonal, which have a Fermi surface which is like this and like this, etc. Enough of those drawings. And now I can only scatter from below the Fermi surface to above, and you can show that if this fellow has one of those orders, that in this direction, the matrix element for scattering is 0, and it increases as you go across here. So now let's look at this little pocket. I can scatter from the occupied to the unoccupied part here, and this scattering increases as I go towards the end. Net result is, now after this is a 1 electron calculation. So no magic is required. You just have to do a sort of complicated second order perturbation theory calculation, or just diagonalize a finite matrix. Okay? And what we discover naturally is that this is done on Mathematica, and if you do Mathematica over the whole Brillouin zone and with not a bit of a poor resolution, you get a Fermi surface in this region, and there's all kinds of things happening here, but the intensity is falling off as 1 over the square of the number of domains. Okay? Now, if you look here, you see this is an absurd thing, right? You have a Fermi R. If you look more carefully, you see that this was really coming from the intersection of those three things, and that these things on this side have very low intensity compared to this thing, and this forms a closed surface. So that's my resolution. So what do I do next? I go to my experimental friends and to say, I have this crazy idea now, please look for it. And this time they did not oblige. Okay? They did, but didn't. So this is the latest of the experiments done here by Dalila Bounois and Philippe and Ivan Sidis and so on. And now you told me 4 samples.
Yeah, but one has no signal.
Oh, that was overdosed?
Yeah.
Okay, so it had signal. That's very important to find a sample. There's no signal. And these had signals starting at specific temperatures, and what they find with neutron scattering, within the limited resolution that they can do it with, what we would have expected is that in this Brillouin zone, there would be, turns out, spots, like that, with decreasing intensity. What they found instead, within their resolution, there was a spot here and here, half 0 and 0 half, okay? Which is the pattern which I said should exist at only the corners, and so should hardly be visible if the domain is big enough. And that thing appears, I'm told, at the same temperature as this, which is the principal black spot, and has 1/10 the intensity. Based on that limited information, these people tried to construct a model which would be consistent with their limited data. It's a bit like if you've gone to an anthropology museum and they discover 6 bones of an animal and then try to construct the whole animal, including how it eats, how it thinks, etc. And they have constructed this, so this central region is large, and also I would have been happy with this thing of order 8 or 10. What they find is at least it's about 15. Okay, and that will give me Fermi pockets too little, except that I've never done calculation of the Fermi surface with a sizable central core. And this should be done. Okay, so not quite what I hoped for. And however, there's another experiment which is also a heartbreaker. This is Lorentz field microscopy. You take a sample, thin film of it, and you do electron transmission through it, and if there's magnetic field in the plane, there's V cross B, and so these things tilt. I don't understand this technique well, but I'm told it's a well-developed technique, and there are various techniques. They can do it apparently by doing a lens and having this lens, the beam fall off the lens in focus, out of focus, etc., etc. They say that they can do it with much higher resolution than the diffraction limit, and they find when they have to invert this thing, calculations. That's the most terrible thing, right? You do experiment, you should directly say here they have to do calculation, and they have come up with this pattern, which is some magnetic field pattern, like magnetic field which is changing directions in the plane. They only look at that, and this length scale is of order 200 angstroms, okay? Whereas I would like it to be 50 angstroms at most. Okay? But the fact that there is a real space observation of the magnetic field pattern is nice, but I thought it was 30 lattice constant. It's more like Philip informed me, 50 lattice constant, while 10 to 20 lattice constant would have been better. Okay? And I don't understand the details of it. It's only the in-field pattern. There should be some in-field also, but they should change their scattering geometry so that it cancels perpendicular. So this is the state of the art. Again, done in wonderful China. So let me summarize my talk. I can honestly say that we understand from the critical fluctuations of the order parameter that I propose here, essentially everything here and here in terms of two parameters for many things, and a third parameter, which is the amplitude of the critical fluctuation. You see that is a constant. I need that in absolute units. I can roughly get that from Phys measurement of the magnetic moment. So I can understand things quantitatively in this region, in this superconducting region. If this thing exists, I've drawn this thing very roughly, precisely what the crossover is. It should be a Fermi liquid, and indeed it's consistent with a Fermi liquid. One can prove, to do a little statistical mechanics, that if there is disorder and the critical point has a dynamical exponent infinity, the effect of disorder is to smear the critical point over a region, okay? And in some other contexts, in highly Fermion, that is observed. And here I need a modification of loop-kind order with a period of a certain size, but what they are seeing is something. There's a period, and there is a magnetic field, it appears, but period is at least a factor too longer than what I would like. So that's the status of understanding of this field. Let me say one thing very strongly. There is zero way of understanding developed in the last 35 years of this region, like linear resistivity, without the particular omega over t scaling that I have emphasized. My young friend, I call anybody who was a former postdoc of mine young. He just celebrated 60th year of Subir Sachdev, and he had come up with this SY model with Kitaev to be the SYK model. I think it's probably wonderful for black holes. I don't understand what the physics of that is in relation to the cuprates. But the fundamental aspect of it is that the fluctuation spectra of it is hyperbolic tangent omega over t or 1 over tau, with which he gets the linear resistivity. Other than that, there has not been any other way. Thank you very much.
Okay, so it looks very much like, cuprettes look very much like heavy fermion, in the sense that, I mean, superconductivity in heavy fermion system, I mean, they are connected to quantum critical points. So the picture of, I mean, what is the origin of superconductivity here in your model? The origin of superconductivity is the presence of this quantum critical point, okay? And this quantum critical fluctuation which explain everything. Is that right?
Certainly about that region, but I want to make, I thought, let me answer a question where I thought your question was going, but it didn't go quite there.
You are meaning that there is a spin fluctuation as well. That's the point. I mean, that you should consider
saying,
spin fluctuation as well.
So the first remark was, this is just like heavy fermions, and we know that heavy fermions have an antiferromagnetic quantum critical point about which there is superconductivity of the D wave variety. And they have linear in T resistivity and T log T specific heat or thermal power. So what goes? What's happening? That's an antiferromagnetic point, and this I say is not, because antiferromagnetism is well separate. And this goes back to the issue of universality in the nature of phase transitions, and this is why I put a paradoxical twist, okay, in my earlier graph. Now, it turns out that in some cases directly, and in some cases with some subterfuge, you can show that all those heavy fermions are planar, experimentally they are planar antiferromagnets, and you can show that antiferromagnets, planar antiferromagnets are, for critical properties purposes, the same as planar ferromagnets, which are X1 model. Okay? And so it's this question that, hey, StatMech is beautiful, the liquid gas and magnets are in the same universality class, and here it seems like the whole class of systems. And in some cases, it's very easy to see. There's just new material, twisted tungsten diselenide, which has linear in T resistivity, etc., etc. And then twisted diselenide is particularly easy to see because of spin orbit coupling, the up spin and the down spin are split by about a volt. So the low energy states are all of a given spin. Given spin at K prime and opposite spin at K prime, but there is no scattering between K and K prime. That's what's believed. In which case the dynamics is purely the XY models. And that's what's happening. Something similar can be said for twisted bilayer graphene, where they observe this linear in T resistivity. So young man, in this case not my postdoc, Liang Fu at MIT and I are just writing a paper on those two issues.
Just to precise that the behavior in this regime, this is universal behavior, whatever the origin of quantum critical point. Just all this behavior linear in resistivity. Maybe I'm not right, just the question.
Yeah.
If all these properties are observed, it means that the underlying quantum critical point, but that's it.
No.
No?
No.
Okay.
I mean, the exponents. For example, if you do experiments on cerium copper to silicon 2, which you can dope to criticality by adding germanium, and on that resistivity has been measured, specific heat has been measured, and you can make large enough crystals to do neutron scattering and measure chi double prime Q omega, and you discover that the resistivity goes as T to the 1.6, the scattering, the chi double, that is the typical Wilson-Fisher extension of classical critical phenomena works for cerium copper to silicon 2, which It's the three-dimensional.
Crossover.
Sorry?
Maybe there is a crossover from classical to quantum.
No, I'm saying in the quantum regime, the prediction is that there's a particular form of kind of a planetary omega, quantum regime. You know, the Hertz, Moria, Millis extension of anti-foul magnets, treating them as isotropic anti-foul magnets, and doing the quantum theory. That works. Okay? Take doped strontium titanate, which has a critical point, one critical point. Resistivity, which is not linear in T, okay? and one understands that by different kind of physics. And so we are getting attuned to being bombarded with materials which behave with T. And if they have both T and T log T entropy, I cannot see any other way than getting the quantum XY. So not enough to say that there is a quantum, but to specify the nature of the order parameter and show the fluctuation power of the quantum XY.
Yeah, maybe there is one more question, then we spent already a long time. So, okay, okay. If you want to continue this
one question from my oldest friend here.
Yeah. I am wondering whether at this level one can say that the pseudo-gap line is really a phase transition, or whether there we are pinning something on the disorder and it's not so clear what is the situation. How can you say whether all the sample freezes at the same time, etc.?
Supposing I look at, let us say, one of the heavy fermion anti-foul magnet with these properties, you can see that there is long-range antiferromagnetic order on one side of the thing, and there, since the period is changed, one can say more convincingly. Yeah? If you believe Philippe's experiment and the second harmonic generation experiment and the magnetic torque experiment, if you believe them, or at least believe them collectively, since they are changing things at the same temperature where the specific heat and ionite shift and magnetic susceptibility are changing, then you have to say that there is broken symmetry. But one has to remember, we are dealing there with a symmetry change of the classical, in the classical regime, of the Cauchless-Thales kind, which doesn't have a specific singularity, and in some sense, it doesn't have an order parameter classically. It has only a change of response function. So it's a little more close.
Yeah, I guess the question is that depending on the technique, the time scale can be different. So in neutron we can see something, but we are in the, it could be dynamic for NMR, for example. So typically it seems that muon has a proper range.
There's an interesting question which almost sounds like a philosophical question, but I'm forced to ask it. I think I put it in my abstract and forgot about it. This issue that Philippe raised. The timescale he measures is long-range order. If you go to timescales 4 order of magnitude smaller, like near-SAR, you see a fairly definite change of relaxation rates at T star, but you do not see a magnetic field, which means that an experiment it's not ordered infinite range or long range in time. Now I ask myself, supposing we were looking at ordinary phase transition, if we had a material we're looking at classical phase transition, and if the correlation length is 100 or 1000 lattice constant, because there are defects around, we say, oh yeah, it's long range ordered, but there are defects, so they. Okay. So I'm forced to ask myself the question, whether there is a concept also of defect in time, like we have defects in space. Now that's a right. One begins to think of, you know, it sounds kind of like, hey, one is getting old and crazy, right? Thinking of defect in time, right? Defects in time exist when you have star quakes or near galaxies and right, bursts of gravitational radiation. But I have to ask, I'm saying there's something to be thought about there, because not only in the case of cuprates, I've come across other contexts in some chromium things where you do not see true long-range order in time if you do things as a function of frequency. So, but I have nothing more to say but raise a question about defects in time.
There is all reasons to get defects in these systems because we know that the doping comes from defect.
Completely, but that's a spatial defect. Now, to get a defect in time, I have a defect which has 0-point motion. Right? If I have a 0-point motion, then that's like a defect in local 0-point motion. That's like a defect.
You cannot distinguish the true static breaking of symmetry from the dynamic. Let's say this transition.
Yeah. So there is some. One has to have some poetic views. One has to become Pushkin and not Putin.
It's to me.
I don't know whom you prefer. I have no idea. Politics.
Pushkin, I'm sure. Yeah, I'm sure.
And I am Ukrainian, not
I am Ukrainian.
Okay, it's very interesting, and I make fun of my friends from that part of the world lately. I've been discovering lately, in the last year and a half, that all my friends who came from Russia are either Jewish or Ukrainian. You start talking to them, they say within the first few sentences, you know, I'm not Russian, I'm Jewish. So, or I'm Ukrainian.
This is less distinguished. Now Ukrainian and Russian.
It's a defect in time. Exactly.
They can even be Jewish and Ukrainian.
Yeah.
Jewish, Ukrainian, like Landau. Landau was from Kharkov.
Okay, so I guess we can close the session. Thank you, Chandra.